13.3 Limits and Continuity. A function of one variable has a limit provided the left-hand limit and the right-hand limit both exist and are equal. There are two approaches that x can take to get to a, and both approaches must yield the same limit. In the same way, a function of two variables has a limit provided every path p to p naught yields the same value. The limits of polynomial, rational, and algebraic functions of two variables exist provided the target point is on the interior of the domain of the function. Evaluate this limit. The function is made up of polynomial and algebraic terms. Find the domain of the function and then determine whether the target point 2,8 lies inside the domain. The domain is all points where the product xy is greater than or equal to 0, which means the domain contains quadrants 1 and 3, as well as the x and y axes. The point 2,8 is in the first quadrant, so we can find the limit by evaluating the function, and we get a value of 100. The limit of a boundary point is L if every interior path yields a limit of L. Evaluate this limit. The point 4,1 is not in the domain of the function, but it is on the boundary of the domain. For the limit to exist, it must be the same value, regardless of the path in the domain we use to get to the target point 4,1. As long as we stay in the domain, the rational expression can be written in this manner. So regardless of what path in the domain is taken, the limit is equal to 4. If you think that the limit of a point on the boundary exists, then use algebraic manipulations to find another expression for the function where you can take the limit. However, if you think the limit of a point on the boundary does not exist, find two different paths to the target point that yield a different value. Suppose we have tried to find this limit and we now suspect that the limit does not exist. We will look for two paths to the target point 0, 0 that yield a different value. A path that yields to 0, 0 is the straight line, where m is the slope of the line. If we vary m, then we vary the path. If we stay on the path y equals mx, then the limit is equal to this expression. For any straight line path y equals mx, the limit is the rational expression given here. Let the values of m vary, and we see that the limit is different depending on which line we use to approach 0, 0. So we say that the limit does not exist. As in single variable calculus, a function is continuous at a point if the function is defined at the point, the limit exists, and the limit and the value of the function at the point are the same. Determine at which point the following function is continuous. The only possible point of discontinuity is the point 0, 0. So we will check there. The requirements are that the function has to be defined at 0, 0, the limit has to exist, and the function evaluation at 0, 0 is the same as the limit. Well, certainly the function is defined at 0, 0. So let's check to see if the limit exists. We're checking this limit. In fact, the limit does not exist. Why? Look at the graph of the surface. Depending on which way xy approaches 0, 0, we will end up at a different elevation. Expressing this formally, if we take the path if we take the path x equals my squared, then on that path the function is equal to this rational expression. For different values of m, that means different parabolas, the limit will vary. Since the limit is not unique, we conclude that the limit does not exist. The function does not fulfill the second requirement of continuity at 0, 0, so it is not continuous at 0, 0, although it is continuous at all other points on the xy plane.